Alright, so in today's video I will be discussing resistors and capacitors in a circuit. So, the simplest type of resistor-capacitor circuit is just a circuit with a capacitor and a resistor. The capacitor will discharge and the current will flow from the capacitor to the resistor, and when the capacitor is fully discharged, there will be no current. But for now, I just want to look at the basics of resistors. So let's see how we can connect the resistors differently in a circuit. So, resistors. So there are two ways to connect: parallel, which there's a battery here, and you get a resistor here, and a resistor here. And so it is important to remember that if this is resistance 1 and this is resistance 2, that in this case the total resistance total, would equal 1 over R1 plus 1 over R2. Alright, and now we can get a series connection, and in this case there will be two resistors connected like this. So resistance 1, resistance 2, resistance total would be in this case just the sum of resistance 1 plus resistance 2. Okay, two other formulas that you need to remember is that voltage across a resistor is equals the current I through the resistor and the resistance. And to find the current through the battery, you have to take the EMF of the battery and divide it by the R total. Now for capacitors. For capacitors, again, you can connect it in parallel. But in this case, we will see that the capacitance will be a little bit different. In parallel, you add the capacitors. So if this is capacitor 1, this is capacitor 2, so you just add the capacitances and you get this total thing. But in series, however, you have series capacitors behave similarly to resistors in parallel. You get that total capacitance equals 1 over C1 plus 1 over C2. Now, an important thing to remember is the charge on the capacitor. So the charge on the capacitor is equal to Q equals CV. That's the maximum capacitor, and usually at some time infinity, this will be the charge on the capacitor. Now for the graphs. For charging capacitors, the charge will start at 0 and it will level off at some constant CV. Charge time. So the current through the capacitor at some time will have the opposite way. Current time. So as t approaches infinity, I will approach 0. So it is important to remember that at some time, after this circuit has been running for a really long time, these capacitances will be reached, and therefore there will be no current flowing, because the charge actually doesn't flow through this. It collects on this side and collects on this side. So for a more detailed explanation, there's another video on this. So I won't go into detail here, but it is important to remember that at some point at t infinity, the current will be 0 and the capacitance will be CV. Alright, so then the energy stored in a capacitor is given by the formula 1/2 Q squared over C. This can also be manipulated into 1/2 QV or 1/2 CV squared. Now let's look at the form of the charging capacitor, the formula for the Q, the charge in the capacitor. The charge is actually given by the formula C, capacitance, times the EMF of the battery times 1 minus e to the power of negative t RC. And I want to look at this RC value. RC is actually a time constant, and from this formula you can see that the larger the t, the time constant, the slower the charging goes. So it will take a longer amount to charge, but if tau is really small, then the capacitor will reach its full capacitance very fast. Now for discharging capacitors, if you just have a capacitor connected in a circuit like a capacitor connected in like this circuit over here, I'll move the paper down so you can see, the capacitor will have, initially there will be a current going through it because there's a full charge on it. The charge, presumably that it was charged before, like we can say that there was a switch here and there was a battery, it was connected to a battery here and therefore charged. And now we disconnect the switch and there's a charge on this capacitance, some charge Q, and now this Q, and Q as from this formula you'll remember equals CV, but through time t, when this is discharging, Q will actually drop until it is 0, and at some time infinity Q will be 0, and then the current in this series only, where there's only a capacitance and a resistor, then the current will actually follow the same path as this charge over here, like this, and as t approaches infinity, current I will approach 0, and in the beginning it will be big. Alright, so now let's look at a problem example. So this is actually a multiple choice example with this circuit, and at first we are asked to find it says here that in the circuit illustrated above, switch S is initially open and the battery has been connected for a long time. So remember, as I said, when the battery has been connected to the capacitors for a very long time, these capacitors are as if not here. This is technically an open, there's no charge passing through here. So what would be the current? Well, the current would be I equals 0 after a long time. With this switch being open, with S open. But then it asks us, calculate the charge on the 10 microfarad capacitor. The charge, if you remember, is given by the formula CV. So in this case, we just take the capacitance, which is 10 microfarads, and times the 30 volts, which gives us 300 microcoulombs. And if you wanted to find the capacitance over this 5 microfarad, you would do the same thing. You would say capacitance times the EMF of the battery, so 5 microfarads times 30 volts. Now, it also asks us to calculate the energy stored in a 5 microfarad capacitor. So now, if you remember from this formula over here, the energy is given by these 3 formulas over here. So since I know the capacitance of the microfarad of this capacitor, right? 5 microfarads, and I know the voltage of the battery, I'll just use this formula over here because I feel that it will be easier. Of course, you could also use this formula over here if you substitute 10 microfarads for 5 and find the charge, but since we didn't do this, I'll just resort to using this formula. So I'll say energy of the 5 microfarad capacitor, so this was the 10 microfarad, and this is for the 5 microfarad. So I have equals 1/2 CV squared, which will equal 1/2 times 5 microfarads times 30 volts squared. And this will give me and this will give me 2,250 microjoules. 2,250 microjoules. If you wanted to find the energy on the 10 microfarad capacitor, you would do the same thing, only substitute this with 10 microfarads. Now the problem changes into that this switch finally closes. So after this switch closes, it might be hard to first visualize what happens to the circuit as a whole. So now we have this passes like this. So the current actually, once the capacitors are fully charged, the current will actually flow like here, and then through this resistor over here, then through this resistor over here. I mean, not the resistor, through the switch over here, through the resistor over here, and then down back to the battery. So even if the capacitors are fully charged, there will be a current running. So in this case, we have to realize that there's a different setup for this circuit. So this circuit, to better understand it, I'll redraw it into another setup. So it will be the same circuit, only slightly different. So I'll leave the 40 ohm resistor here, but since now this 40 ohm resistor and this 20 ohm resistor are in a series, it is important to realize that. So, but this resistor and this capacitor are in parallel. So 5 microfarads, and now 10. And 20 ohms. And it is connected to a battery of 30 volts. Okay. So now that we have redrawn this series in this circuit in this way, it is much easier to see what is happening. So now when the question asks us to find the to calculate the steady-state current through the battery after a long time, so the I over here, we have to realize that the current will be traveling this way through the resistor over here, and then through the resistor over here, and then down over here. So first we have to find after a long time. And again, this is important because after a long time, because that way we know that there will be no charge going through the capacitors. So after a long time, we have to find the total resistance, and the total resistance of a series, if you remember, is just R1 plus R2. So in this case, we just add 40 ohms plus 20 ohms. And so in this case, it's 60 ohms, and we get that I current equals the EMF of the battery over R total, which is 30 volts, divided by 60 ohms, which is 1/2 of an ampere. Now we have to calculate the final charge on the 5 microfarad capacitor. So the final charge here, if you remember, then the voltage in a parallel construction is the same over here. So if we put a voltmeter over here and a voltmeter over here, it should read the same thing. So voltage across this capacitor will equal the voltage across the 40 ohm resistor. So what does that tell us? So this tells us that the formula Q equals CV. This V is not the EMF of the battery, it's the voltage across the capacitor and across the resistor, and also equals to the resistor. So how do we calculate this V? Well, this V will be given by the formula V for the 40 ohm resistor, which equals I through that R through that resistor, and times the resistance. So that would be 1/2 amperes times 40 ohms, which will equal 20 volts. So now that we know the capacitance and the voltage across the capacitor, we can calculate the charge stored. So that would be 5 microfarads times 20 volts, which would give us 100 microcoulombs. Okay, now the last point is we have to calculate the energy dissipated through the 40 ohm resistor after it has been running for 60 seconds. So and after steady state. So all of this is happening after steady state. So after steady state, and what that means is that there's no current running through the capacitors. They have been fully charged. So to find the energy dissipated through the 40 ohm resistor, we have to first look at the power. So energy equals power times time. So after 60 seconds. So the power is given by the formula. Did I write it here? Oh, I thought I wrote it here. Well, let me just give you the power formula. The power formula is equal to I squared R, and if you manipulate this, you can actually get that it will also equal to IV, or V squared over R. Yep. Okay. So in this case, since we look at what we know the resistance, and we know the current. The current will be 1/2 amps. So we can pretty much use this formula over here. So then we have that 1/2 amperes times squared times the resistance, which is 40 ohms, and we will get that 1/4 amperes squared times 40 ohms. Oh, and times 60 seconds, of course, I forgot. So this is just the power. In this case, I'm just finding the power. So the power would be just 10 watts, and watts is joules per second. And now to find the energy, we will say power times the time, which is 10 watts, and then times 60 seconds. So the total energy that's lost through heat is 600 joules.
Alright,